Hey guys, welcome back. Today we're just going to do a little bit of quiz review. So no new content in this video. We're just going to kind of go over some of the problems we've seen this week, which are just the basics of graph theory, like identifying vertices and edges and the degree of vertices, applying some of those vocabulary terms, and then doing a little bit of Dijkstra's algorithm. All right, so here we go. So let's say we have a town with 7 bridges as pictured below. So here's this town, and we want to create a graph that could be used to determine if there is a path that crosses all bridges once. All right, so the main thing here is it wants us to create a graph. All right, so we're creating a network graph. And the way that we do that is we allow in this scenario, we're going to allow the towns, or not the towns, but the land masses here to represent a vertex, right? So like this entire landmass up here, like this entire white area up at the top, we're going to reduce that down to a single point. All right, so I'm just going to draw a point, and that's going to represent this whole thing up here up north, right? We'll call that A, right? So make sure you give your vertices a name. Right, and I'm going to make sure I go through and do the same thing, right? So there's this one over here, so we'll put it over here on the left. It doesn't really matter how far or how spaced out it is. You might want to give yourself some space, right? So I'm going to let that one be B. We got one here in the middle, right? So this particular landmass, and we'll put that here in the middle, and we'll call that C. And then over here, we have another landmass. We'll call that one D. And then we have this one down here, right? The south end of town, big landmass, and we'll put that one down here and call it E. Right? So we've taken all the land masses, we've reduced them down to a single point, which we will call vertices, and now these land masses are connected by bridges. Okay, so for instance, over here between B and A, and I'll just go ahead and let me get rid of all these squigglies here, and let's just label these land masses so we can keep track of them. Right? This was A, B, E, this was D, and this one was C, right? So we can see there's a bridge here connecting landmass B and landmass A. All right, so I'm going to come over here and I'm going to draw an edge that connects B and A, and that edge represents that bridge. All right, and also in B, there's another bridge that connects B and E. All right, so I'm going to draw an edge from B to E. All right, and we maybe go back up to A, and there's a bridge that goes from A to C, so I'll draw in that bridge. And then there's another bridge from A to D. So I like to just go to a landmass and say, okay, look, there's 3 bridges coming out of landmass C here. I've already got the one going to A, so I'm going to get the other 2 bridges, and both of those bridges go to E. All right, so I'm going to draw one bridge to E, and then I'll draw a second bridge to E, and you can curve it, right? It doesn't matter. Yeah, I curved it because I don't want to draw one edge on top of another. So the edges that you draw into your network graph, it doesn't matter if they're straight or curved or whatever, just as long as they connect one vertice to another. All right, so I've got 2 bridges coming off B, I've got the 3 coming off of A, I got 2 coming off D, so D needs an edge that goes to E. There we go. And then we go down here to E. So E's got 1, 2, 3, 4 bridges, and I got 1, 2, 3, 4. C's got 3, 1, 2, 3. B's got 2. So you notice I'm just going around and making sure that I didn't miss any of the bridges that connect. All right. So this would be a good network graph right here that represents this situation. And then it says it wants you to use it to determine if there's a path that crosses all bridges at once. All right, so for a question like this, remember it wants you to try and cross each bridge exactly once. So maybe you grab a highlighter and you're like, okay, well, let's see if there's a path. Now, a path can start and stop anywhere. All right, so we don't have to, so like for instance, if I start at A, right, I don't have to end at A. I can end anywhere I want as long as I use each bridge once. So I don't know, let's give it a try. So I'm going to go from A to D first. So I use that bridge. And then from D, I only have one option. I'm going to go to E. And then I'm going to go to, let's go to B. And then from B, we would have to go to A. And then from A, we would have to come down to C. And then C down to E. And then E back to C. So there is a way to do it. So, and I got really lucky there and I found it. So let's write that path down. Okay, so I think we started, let me get my pen. There we go. So I think we started at A, right? We went to D, and then we went to E, and then we went to B, then we went back to A, and then we went down to C, and down to E, and then back to C. And I think that got them all, right? So if I think there's 1, 2, 3, 4, 5, 6, 7 bridges in my path that I described here, and I got 1, 2, 3, 4, 5, 6, 7 bridges. So I got them all. There we go. All right. So let's take a look at some of these other problems, right? So number 2 is just like basic vocabulary stuff, right? Like find the degree. So you might need to remember what the degree of a vertex means. And the degree of a vertex just tells us how many edges are connected to it, right? So here's a vertex, and so this vertex would have a degree of 2 because it's got 2 edges connected to it. So I'm going to label these for my own convenience, right? So A, B, C, and D, and then we'll just come over here and list their degrees. Right, so A's got 2 edges connected to it, so it has a degree of 2. B has 1, 2, 3, so B has a degree of 3. C has a degree of 2. And D has only 1 edge going to it, so it's got a degree of 1. Okay, and that's all we would have to do for that problem. All right, number 3 is much the same thing, right? So again, I would start by labeling your vertices. So we got A, B, C, D, and E, so we got 5 vertices. There we go. And we look at vertex A, right? So it's only got 1 edge connected to it, so it's got a degree of 1. B has 2. C has 3, so 1, 2, 3. D has 2. And then E has 1, 2, 3, 4. There we go. All right, let's keep going. All right, so which of the graphs are connected? So this is another one you might need to go back to the notes and read the definition of what it means for a graph to be connected. But the way that I remember it is I think I should be able to start at any vertex and get to any other vertex, right? So for instance, in this one, if I said this was vertex A and I called this vertex B, is there a way for me to get from A to B, right? So I could go here, here, here. So I could get to B, right? And let me erase that. And let's say I named some of these other vertices, so A and then B, C, D, and E. So I was able to get to B. Could I get to C? Yes, obviously. Could I get to D? I could get to D by going that way. I could also get to E, right? So this is a connected graph. I can get from vertex A to any other vertex on the graph, right? But now over here, right, I've got A, B, C, D, E. Let's say I wanted to get from vertex A to D. Well, there's no way for me to do that. There's no edge that gets me from this part of the graph to this part of the graph. All right, so this one is connected. This one is disconnected. This one is connected. All right, and you're more than welcome to try that one out. Let's see here. So which of these graphs are connected? Let's see. So if I go here, let's call this A. If I go down here, let's call this D. There is no way for me to get down to D. So this is not connected, right? Let's say disconnected. This one, right? So if I were calling this vertex A, and I should be able to get to any other vertex. So I can get to this one. 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 If I had taken a different turn here, I could get to this one, and then to this one. So this one is certainly connected, right? This one is disconnected, right? And again, so like if I were trying to travel from, let's say, vertex A to vertex B over here, I could try my best, but there's no way for me to travel the edges here to get to the edges over here. So this one is disconnected. All right, Last problem here, I'm going to do one more. This should be a short example of Dijkstra's algorithm finding the shortest path through a network graph. So there are several other examples that I've done in the last 2 lesson videos. So if you need to see more examples, make sure you check those out. But I'm going to do one more just for your benefit. And let's see where we need to go. All right, so travel times by rail for a segment of the Eurail system is shown below with the travel times in hours and minutes. It looks like it's actually only in minutes, right? So we'll get rid of the hours. So it's in minutes. And find the path with the shortest travel time from Bern to Berlin. All right, Bern is here. So we'll say Bern is the start and Berlin is the end. So we're trying to get from Bern to Berlin in the shortest amount of time possible. All right, so remember we mark the end with a 0. And then we look at all of the edges that lead into the end. All right, so I've got 2 edges that lead into Berlin. I've got this 370 and this 345 out to München. Okay, so I'm going to go to München and I'm going to put a 345 on München. I'm going to put a 370 on Amsterdam. And then we would consider Berlin to be visited, right? So that way we don't trace any of the edges back to Berlin. And then we look at any vertices that we have marked. And so I'm looking at München. It's the shortest one, right? 345 is shorter than 370. So I'm going to come down here to München. And I'm going to look at the edges that lead into München. There's 2, but one of them leads back to Berlin. So I don't need to do that one. But here is this one. It is Frankfurt. And Frankfurt is 190 more minutes, right? So we do 345 plus the 190. And that'll get us... total amount of time here. Let me pull up my calculator because I don't want to do that. So lazy right now. I should be able to do that in my head, but I'm not going to. So 345 plus 190. I got 535. There we go. And we're coming from München, so I'm going to put an M there. And don't forget to leave your bread trail here, right? So these both came from Berlin, so I'm going to put B's on those. All right, so now again, München has been visited. I analyzed both edges leading into München. So now I look at my 2 vertices. Right now, Amsterdam is the shortest one. So I'm going to go Amsterdam. I've got 2 edges, or actually 3 edges leading into Amsterdam. One goes back to Berlin, so we don't need to do that one. So let's do this one to Paris. I've got 370 plus another 85 minutes. So that's going to be 455. Coming from Amsterdam. Put an A on that one. And then here we've got 370 plus 240, which is 610. All right, so 610 is longer than what we already have there, so I'm not going to replace the time that I have at Frankfurt. All right, so Amsterdam is done. All right, so we're still analyzing, right? I got 2 vertices. 455 is shorter, right? And it's only got 2 edges. One goes back to Amsterdam, which we already visited, so we're not going to do that one. So we got to do 455 plus 115 to Lyon. I think that's how you say that. Lyon or Leon. I think it's Leon. All right, so 455 plus 115. All right, a little mental math here. So we got 570. And that's coming from Paris. There we go. All right, Paris is done. Okay, so now look, 570, 535. The 535 is currently shorter, right? So I'm going to do 535. I've got 3 edges coming into Frankfurt. 2 of them go back to visited city, so I only need to do this one to Bern, which is where we're trying to get to. All right, so we do 535 plus 235, which is 770. Coming from Frankfurt. And then we'll consider that one done. All right, we have 1 left. That's this train coming from Lyon. All right, so we got 570 plus 230. So 577, that's 800. That's longer than what we have here. That's longer, so we're not going to replace it. So Lyon is done, and now we have our time. So let's trace this back, right? So we're going to start in Bern. I'll write this out down here. So we got Bern to Frankfurt. Bern to Frankfurt, and then once I'm in Frankfurt, it tells me to go to München. And then from München, it tells me to go to Berlin. I spelled that wrong. There we go, Berlin, and it's going to take a total of 770 minutes to complete that trip. All right, we already calculated that there. All right, guys, so that is Dijkstra's algorithm. Hopefully you found that example helpful. Give the practice problems a try. Make sure you get ready for that quiz tomorrow. I want you all to do well. Have a great day.